Hello, this is Alan Folmsby here, speaking to you from Hawaii, and it's the Christmas season, so I have kind of an informal setup here, and I'm going to go over to the backyard view here to talk a little more. Hello, December 2019. It's quite a cool day today. It started out like 69 degrees, way below what I'm used to. So today I'm going to be talking about the chemical bond and how physics is now getting a new foundation for the bond. Now the bond is really a flux in terms of units of measure. And much like an ampere is coulombs per second, that's a flux. Since a coulomb is near a square meter of something, it's an area. And the Weber is also a flux of magnetic flux. And the Tesla is magnetic flux per square meter. And the bond is also a flux, which flux squared is energy. So it's compatible with Schrodinger's equation, for example, where he's using the imaginary complement, the conjugate, for the multiplying the wave function squared. So what I'm going to be talking about is the Mach bond. And this is where I put together a model in using geometry and showing that there is some kind of validity to having a mock-up of a chemical bond, and that when I talk about angular momentum can be the non-crossing law, making the winding and unwinding of these dimensions around a common gradient path. So I'm going to go back to the PowerPoint slide now for a minute. And you can see I'm going to be using the two-dimensional bond of a steel tape measure, which I purchased. And in some ways, it is unrealistic for an oxygen molecule bond. But in other ways, it is realistic in a limited number of geometric ways. For one thing, it can easily form a vortex shape, much like a bond or a magnetic field flux, where the nucleus will be the small end of the vortex, and then there's an expansion outwards where the eddy current of electrons is the far end of the vortex. All right, so the bond I'm going to show you, in terms of units of measure, it's the length of velocity, and that gives you square meters per second, just like a Weber, an ampere, and other fluxes of a property that's different from momentum. An ampere of current is not momentum, it's a flux. So you could use a rope for the experiment that I'm going to show you. And I'm going to turn around the camera for a second, and then I'm going to put together a rope where you can see a bond forming between the two electrons and two nuclei. All right, I turned the camera around here, and you can see in this picture here that there's a chair, and I'm going to have a string coming off of that, and then it'll wrap around with another string with a weight on the end, and they will wrap around each other like a bond so that it's hard to pull apart until they come the other way, because there's a springiness in either a string or a steel tape. So let me get that together for you now. And when I put together this little string or rope type of simulation here, mock-up, I'm going to be then moving on to a tape that can enforce the vortex cone shape against gravity. So in other words, in an atom, they don't have gravity distorting their experiments. It's more of a vacuum situation. But we can have a slow rotation of these tapes or ropes around each other to make a mock-up of the oxygen molecule O2. And in this way, I want to show that there's an equilibrium distance that if you get farther apart, it'll pull together, but if you get too close, it'll push apart. So basically, this type of atomic scale. And now to bring it back to the overall theory that I've been providing, here's iron, the picture of iron 57 nucleus. There's 26 protons in this picture in black, and a bunch of white neutrons. Now, there's also 26 electrons associated with this atom, but they're 1 mile away at this scale. So I've changed the scale around here for iron. You see the proton rings here, now they're green instead of black. And as you can see, there's red lines. There's 26 red lines coming from the 26 protons, and they're all going to the electrons 1 mile away. Now, because we brought one electron into view, so say it's in the far distance 1 mile away, but you can see it here right behind the nucleus for our viewing pleasure. Now, the blue electron there is connected by 2 black space dimensions and 1 red time-like dimension, and these are making all interactions between the electron, whether it's in another bar magnet 10 feet away, or whether it's in an atom close up inside this bar magnet here. It still is deterministically paired up with that. And these 2 dimensions is like the tape. So when I use the steel tape measure later, you're going to see that you get the 2 dimensions that are enforced by the proton interactions, but 1 dimension where the electron's free to move, and the tape can bend easily in 1 dimension. All right, so I'm going to set up some things here for the Mach bond now. All right, I got my mobile microphone here so I can walk over to the equipment in the Maui Theoretical Physics Laboratory. All right, we see the manganese nucleus here is very different shape than the iron. I've been showing you iron all along during all these pictures here. For example, the famous Discovery model mock-up here. It's so simple compared to manganese, and therefore that's why it gets the powerful magnetic, ferromagnetic property of iron. 2 rings of protons in white, and they're coaxial with each other. Now manganese, on the other hand, is not ferromagnetic. But you can see it has 1 ring of 10 protons anyway. And this is built very differently than iron. See, it doesn't have coaxial rings on the other side. It's kind of quite a collection because the cube at the center of manganese only has 2 layers, and the rest of them are on top of this cube. Whereas iron has 3 layers in the cube, like this. So with the 3 layers, the iron nucleus is larger in the center, and it's not as flat as manganese. So this is element 26 cube. Now element 25 is manganese, so it only has 1 fewer proton, and yet the shape is completely different. It's a transition from the small cube, like this. So manganese has a small cube at the center with only 2 layers, where the green protons here and white neutrons. So that's very different than the 3-layer cube in iron for element 26. And that is why iron is ferromagnetic and manganese is not. On the other hand, manganese has what I would call itinerant proton rings. So there's the proton ring with 10 protons, and on the other side, that ring has been ruined like in copper. And that ring, you see, has been shorted out with that additional number 25 proton there of manganese. That one on top of element 24 ruins this ring. It's no longer even a ring. It's the axis is shorted to the ring. So this, I theorize, provides an itinerant proton ring current so that manganese, strontium oxide, or other compounds can be ferromagnetic, even as an insulator, or different molecules that do not have iron or cobalt in it. So here's the partially built iron for the holiday toy opening. I know it's Christmas time, so Christmas time travel is possible at this time of year. And this is 1 little lithium on top of the cube, and it starts to make the ring. And celebrations are beginning already here in Maui. In fact, I've obtained a turntable for your viewing pleasure. I can just put this on top of this here, and I'll zoom in on that. And I'll be able to turn lights on and off too. Oh, great. Camera work here is zooming in and out beautifully. And then I can just rotate this model around slowly on a turntable without getting my fingers in the view. Well, fingers are not as bad as they're all cracked up to be anyway. Let me turn off this little light here because I think it's interfering with the viewing pleasure. I'm going to zoom in a bit here. Oh, nice. December 23rd, tomorrow's Christmas Eve. So I opened up this present in Christmas time travel. Christmas time is a very special time. And let us remember, Jesus Christ was born 2 days from now, 2019 years ago. Let us pray. Peace on earth. Amen. There it is. The manganese model, mock-up. I'm making a mockery of reality here. But not of physics. No, this is just a stepping stone on the path to a greater wisdom. Now, this type of model is made with geometric reasoning. It could not have been made using conservation of energy. That's ab initio in standard science. Now, the Schrodinger's equation would never have provided the shape of iron, which I'm going to put up here now. All right, I'm going to zoom in even closer on this one. This is fun. Okay, we're back over to the laboratory again. I'll try not to block the lighting from the window. But it appears to be centered in the camera. Iron 57. Now, it's hard to see the cube in the midst of the large-scale structure. And this is one of the things in physics you see over and over. Small things repeated in bigger scales also, like ferns or crystals of iron pyrite and things. Now that large loop you see there is really just a cube on that center dot. That axis there is the corner of a cube. And I have a model of that sitting right over here. So let me put them side by side and you can see the orientation of these things. There, you see how the axis on the iron is just like the corner of the cube here. And there's 8 protons in the cube. With 3 layers, of course, there's 27 protons and neutrons on the right cube here. And the axis here is the same as this one over here on the cube. And then the other one on the right side here is the same as this one here. And that if you realize that this is just 6 lithiums on top of this cube, then you would be on the path to a deep understanding of matter, and that this is the correct theory of nuclear structure. But now getting back to the chemical bonds, we'll see. I'm going to bend over this thing here briefly. And we begin to see the bond. So each of these white protons would then have an electron connected through it, through a bond. So let's just stick this one on here. There, it's all just holding together. That bond is then sticking up onto an electron a mile away. And then if gravity will permit, I'm going to put another one on there. So it's hard to pick up these tapes. Uh-oh, fell over. Oh, there's one. See, edge on, you can't even see it. Like superconductors. These layers, these thin layers of a two-dimensional thing are strong in 2 dimensions as they're driven by a proton, yet the electron's free in that 3rd dimension, like the steel tape. So it's able to bend that way freely. It's like a free electron at the end of this. And then that bond is connected to a proton here on the ring. And the ring is like it's spinning in the vortex of all these bonds going around in a circle. Makes a V-shaped vortex. And geometrically, this type of simulation is going to be put together to be accurate in some ways and inaccurate in most ways. But I insist that there are ways this is accurate. All right, so I got the bond able to stick in there with gravity holding it together. So I'm going to just back off on the zoom. Oh, that's better. Yeah, you can see that the bond is bending away, and it's going to form an atom. And the atom will have a characteristic size of less than 3 angstroms. All right, so now the tape like that is good, but you know, I could use a rope instead of bonding. Instead of making miles of bonds with a tape, why don't I just use a rope? There, I've got a nice red rope for Christmas. I'm going to place it carefully in back of the tape. And then I also have a green rope I'm going to bring over, and we'll work with that one. But then I'm going to put aside the green and secretly work on the red rope in front of the camera without talking. So don't tell anyone about this, because the rope is really not a good way to model it. All right, now here's the green rope for Christmas. And we're going to be silently working on a bond mock-up. All right. I don't think anyone's listening right now, but here's the red rope. And if you think a steel tape measure is unrealistic, you're right. A bond really has other characteristics than a length, a springiness, a one-dimensional freedom in 2 dimensions of driven length. That's right, it's realistic in a limited number of geometric ways. But why are we going to the rope? Just, it's easier this way to mock up things. All right, I'm working on the rope now. Okay, I'm working on the rope. I'll be back in a minute. Okay, I've placed one of the ropes over in the area where the camera is going to be turned really soon. And as I turn the camera, I'm going to be real quiet. All right, I know tomorrow's Christmas Eve, but I'm going to use this red rope here today. Here it is. over here by my hand, there's a red rope hanging straight down, and the chair is sitting on top of it, so it's pretty stiff. Let me tighten up the bottom a little bit so the rope is pretty stiff, and I'll put a second rope on it with a weight attached to that rope, and that will wrap around this one. All right, that represents one atom of oxygen. That red rope is like oxygen. Or I have a white rope here, and it's very flexible, a little nylon thing. Well, let's see, hold on. Well, that was pretty good. I didn't even put a weight on it. Hold on, I'm going to put a weight on this thing right now. Okay, I'm back. I got a big magnet, and it's stuck on a little alligator clip. I'm going to try and rotate that around the big rope. All right, so the successful experiment was there. On Friday, I'll be back. I'm on every Monday and Friday now during the holiday season. And so when I get back, I'm going to describe for you the successful experiment that you just witnessed. Why it's successful, and why am I not just sitting in front of the camera instead of bending around like this? Well, because it's a relaxed atmosphere during this retreat. I'm in retreat today, see? Look, I'm very laid back in my cushy chair here in the center of Maui. And thank you very much for stopping in. As I said, I'm going to give you some more information about what you just saw there. The rope going around one way, and then the other way, making a vortex in the same geometry as a chemical bond or a magnetic bar magnet with a proton in one bar and the electron in the other bar magnet. See, it's not just atoms that involve these dimensions. This could be the proton in one bar magnet, but that electron there is in a different bar magnet, but it's paired with this magnet. And that's how reality works, because it's the correct theory. Thanks a lot. I got to go now. Bye.